As you sit here watching this, you are being bombarded by air molecules. They are slamming into your skin all over you. Of course, an air molecule is not very big, it's not very noticeable, but there are also a hell of a lot of them banging into you. And it turns out that if you add up the effect of all the collisions of all the air molecules slamming into, it's absolutely a colossal force. In fact, it's called air pressure, and it's a force of about 100,000 newtons per square meter. Newtons per square meter being called pascals, the unit of pressure. That's colossal. That's like tons of force on your body. Wow, you're crushed flat by the relentless bombardment of all these particles. Well, luckily, the force is very well balanced. The atoms bouncing off one side of you and bouncing off the other side of you are exquisitely equally balanced, otherwise you'd be pushed over. Normally we live in the middle of this colossal pressure and never even notice it. There are only a few situations where you notice it. One would be trying to open the door on a submarine, so you've got water outside at a much higher pressure than the air on the inside. Then you'll realise the effect of the pressure. Or on a spacecraft. Another practical issue is when you're scuba diving. Let's say you're swimming along underwater, gas tank on your back. The gas tank has a pipe that goes to what's called a regulator that sits on your mouth, and that delivers you air at the same pressure as the water on the outside. It has to, otherwise you couldn't breathe it. If you had to try to suck in air that was at 1 atmosphere when you're at 2 atmospheres pressure, there's no way your lungs would have enough muscles to overcome it and suck it in. And this can be a problem, because let's say you're floating 10 meters underwater. Your lungs will be full of air at double atmospheric pressure. If you then panic and swim for the top really fast, here's the top of the water, without breathing out as you go, the air inside your lungs, as double atmospheric pressure, will no longer be balanced by the pressure outside and will actually rip your lungs apart if you do that. One of the first things they teach you in scuba diving is keep breathing. As long as you're breathing constantly, they'll keep the pressure inside and outside the same, and then it's safe to go to the surface. If you forget to do that, you won't know anything's going wrong because there are no nerves inside your lungs until your body is ripped apart. Yeah, anyway, let's get on to some more pleasant stuff. Can we actually calculate from first principles what air pressure should be? Well, let's imagine we have n molecules per unit volume. The kinetic energy along any one axis will be half kT. So let's say they're going left-right, there's going to be a half kT there, and another half kT vertical, another half kT in and out of the screen. But if we're looking at what hits a particular wall, let's say we put a wall over here, all that matters is the velocity in this direction. Now this half kT will be equal to their kinetic energy in that direction, so it's half mv, let's call this the x-axis, mvx squared. So we'll find that the typical velocity is going to be roughly root kt over the mass of a typical molecule. Okay, so that's how fast the component of the molecule's speed in the direction of some wall, and it's pretty close to the equation we came up with earlier for the average speed. It's an average. Some molecules will be going faster, some slower, but it's a reasonable average. Now, how many molecules are going to hit the wall in a given time t? Well, what we can do, if we have, here's our wall, I'll try and draw it in 3D now, and here's a unit area on it. We can imagine an imaginary box of length Vxt. And if a molecule's in this box and it's going towards the wall, it's going to hit that bit of the wall within time t. If it's in the box and going the other way, it won't. We'd expect about half the atoms to be going towards the wall and half away, so you'd expect the number of atoms hitting the wall in a given time would be about a half of the number per unit volume n times the volume, which is an area of 1 times Vt. Now, how realistic is that? We're just assuming here the molecules only hit the wall and not each other. If t is short enough, that's going to be true. If this length here is less than the mean free path, then it's going to be mostly true. Even if it's bigger than the mean free path, the molecule here might bounce off another one and ricochet off. But that also means the ones that are coming out might ricochet back on again. So it's not going to make much difference. So it's probably not unreasonable. Now, what are the molecules going to do when they hit the wall? So we've got our wall, and we've got our molecule. Let's assume it bounces off elastically. Anything else would violate conservation of energy. If the wall was actually cold, then they might bounce off with less speed than they came out. But if the wall's the same temperature as the gas inside, then they should bounce off at about the same speed. That's quite reasonable. Another approximation I've made is I've ignored the fact that molecules are actually moving in all sorts of different directions, not just straight towards or away from the wall, but we're just looking at the component of velocity in this direction. The fact that they're having a glancing blow doesn't matter, because all we considered is the component in and the component out. Okay, so let's say a molecule does bounce off the wall. It's going in at speed vx and comes out. So the change in velocity, the delta vx, is going to be 2vx. So it came in at velocity v, went out with v in the opposite direction, so the change is that. The acceleration, therefore, is going to be over some time t. It's going to be the change in velocity, 2vx, over the time. And if you use F equals ma, we find that the force is equal to the mass times 2vx over t. Now, it's not going to be a constant force. I mean, for each molecule, it's going to bounce off at one particular moment within time t, having a very big force for a very small time. But here what we're doing is we're averaging over the entire time. So if you plotted force versus time for each individual molecule, there's going to be whoa, and then another molecule is going to be whoa somewhere else. But we're averaging over all the molecules. It should come out as about that. Now, if you plug some numbers in, we'll find that the force is equal to the mass of a mole times the number hitting, half n a vt, where a is the area of the bit of the wall, times 2v over t. So we've got a v squared that equals n a v squared. We had an equation for v, it's vx squared. So it comes as m n a k t over m. So the masses cancel, and we come out with n a k t. Now that's the force, so pressure is just force divided by area equals n k t. Now n here is the number per unit volume. Big N is number per unit volume. We can also define small n, which is just number of molecules. So n, big N, is just n over v. So we can rearrange this as p v equals little n k t. And you may recognize that that's the equation for the pressure of an ideal gas. It's sometimes written in the form PV equals mRT, where instead of having n the number of molecules, you have m, which is the number of moles, and you have to change the constant to compensate for that. But these are actually just the same equation, it's just different units. So does this equation work? Consider 1 cubic meter of air. We worked out it had about 10 to the 25 molecules. It's 2.6 by 10 to the 25 molecules. So you can work out the pressure. At 300 K, you get a pressure of about 107,000 pascals using this equation, which is pretty close to actual atmospheric pressure. So this rather simple equation works. We can now understand where atmospheric pressure comes from. just a constant bombardment of vast numbers of molecules, and our simple approximation that the energy is half kT gets the pressure right to within 10%. Pretty amazing.